All right, good morning, everyone. My name is Partha Nageshwaran. Before I get started, I quickly want to acknowledge some of the key members of the Bloomberg team that are involved with Spark initiatives. Over here, we have Joe David. Joe, if you'd kindly stand up for a second. He's one of the key contributors to some of the implementations as well as ideas that I'm going to be talking about. We also have Andrew Foster in Lugano, Switzerland. He couldn't make it here, but I think he's enjoying Switzerland a little more than San Fran. And there are other members, Nimbus Gauhausen in San Francisco, Tracy Liang, and Shubham Chopra, who actually had a meetup yesterday that some of you might have been at. OK, so let me get started. My name is Partha Nageshwaran. I'm an R&D lead at Bloomberg. Along with my colleague Sudarshan Kadambi, who's an architect, we're going to be talking to you about various Spark serverization-related initiatives that are underway at Bloomberg and associated innovations that have come along the way. Over the last several months, I've been architecting a cloud-based low-latency analytics platform that leverages several technologies, Spark being one of the core technologies. And this effort has now culminated in the creation of what is known as the Bloomberg Spark server. In essence, we've basically taken a container-based approach to host Spark applications inside of a runtime. And over the next few minutes, we'll be talking to you about the various puzzle pieces that make up this runtime that's referred to as the Bloomberg Spark server. By way of motivation, even as Spark was widely accepted inside of Bloomberg many moons ago, several standalone Spark applications started mushrooming, right? And each of these standalone Spark applications would have executed on standalone clusters, in essence creating siloed environments. The challenges posed by these siloed environments are significant, right? On one end of the challenge spectrum, you basically have significant amount of redundant effort. So imagine the amount of work each of these Spark applications would have had to do relative to implementing the same reusable functions, such as currency conversion. Right? In financial analytics, currency conversion is a very common task that needs to be applied pre or post analytic. And pretty much every one of these standalone applications would have had to implement the transforms and the actions relating to currency conversion. But it doesn't stop there. The redundancies go even further. Consider for a minute hundreds, if not several hundreds of RDDs and data frames which we have in our Spark environment. Each of these standalone applications essentially reference quite a few of these hundreds of RDDs or data frames. And they'd have to code lifecycle management code to instantiate and manage these RDDs. Extremely inefficient. Right? But setting inefficiencies aside, let's go to the challenge spectrum on the other side. Each of these standalone applications would have had to solve significant technical problems on their own. Consider the problem of reconciling metastable data with streaming data. Right? In financial analytics, this is a common problem. Right? Metastable data typically covers data from the market yesterday back 40 years, for instance. And they tend to not change very often, but they do have changes. On the other hand, streaming data captures intraday data that flows in from the market. And any query needs to reconcile these two data, otherwise we're not giving the freshest possible results to our clients. And each one of these standalone applications would have had to solve this reconciliation, be it at ingestion time or be it at query execution time. And this is not a simple problem to solve. A better approach would be to actually have this solved at the infrastructure level, i.e. at the Bloomberg Spark server level, which in essence is what we've done and we're refining. Now, there are other challenges. One particular challenge that comes to mind is the fact that these siloed environments inhibit ad infinitum composition of analytics. How do you take the results of one silo's output and pipe into another silo's input when you're talking about interactive analytics? Right? So it's challenging. The synthetic boundaries introduced by these silos actually almost make it impossible in some cases. So any serverized environment had to solve for all of these challenges and a whole lot more. And we're going to talk to you about how we solve some of these problems and some of the innovation associated with those. All right, let's stay with the theme of compositional analytics. In the financial analytics world, compositional analytics is kind of a bedrock. It's just assumed to be there. And here's a simple example of a compositional analytics. This is just a two-level compositional analytics. But in general, any serverized Spark environment has to solve for arbitrarily complex compositional analytics, right? Which we have achieved. In this particular example, we are showing you how to compute the decile rank of the relative strength index for some equity stocks. Don't worry about what RSI or relative strength index is. It's just some formula which translates to a set of Spark transforms and actions. Decile ranking, likewise, is a set of transforms and actions as well. And by compositional analytics, what we're talking about is at execution time of this query, you want to be able to kind of union the transforms and actions from both of these functions and then apply the union transforms and actions onto a data frame, for instance, to get some results. Now, the analytic could change. So someone else, a different use case, might want the percentile on RSI. The concept is still the same. It's still composition, except it's a composition of different sets of transforms and different sets of actions, right? You can replace RSI with ROC or return on capital, and the story goes on, right? Now, throw into this mix user-defined analytic functions. Now, there can be arbitrarily complex analytics logic captured as Spark transforms and actions that are available to be composed in this ad infinitum composition model that I envision, right? So if you actually allow for user-defined analytic functions, I contend then that pretty much any analytic can be expressed as a formula rather than having to write code, all right? So how did we solve for compositional analytics, and what are the characteristics that the Bloomberg Spark server supports relative to compositional analytics? Well, first off, we came up with a very simple specification. If you want your analytic function to be composed ad infinitum, it basically had to comply with a contract. You take optionally a data frame or multiple data frames as inputs, but you must return a data frame as an output. Very simple contract, right? So here's implementations of RSI. If you understand it, great. If you don't understand it, no big deal, right? And similarly, you've got the decile function implemented, takes a data frame, returns a data frame in this particular case. So user-defined analytic functions would also have to be compliant with this sort of a contract, right? Now, once you create these functions, what does the Bloomberg Spark server provide by way of infrastructural support to do this ad infinitum composition? Well, the first innovation was to introduce the notion of function transform registry. At first look, this is just another naming server inside of the Bloomberg Spark server, but it's a tad bit more, right? What you do is you register your functions with a name and associate the name with the Spark implementation for that function. But the beauty of this is that you can also register named functions that reference other named functions. So off the bat, in the infrastructure, we actually provide the ability to compile these named functions that reference other named functions. And so this compositional capability is baked right into the first puzzle piece, if you will, right? And obviously, this function transform registry has to allow you to bind and look up these named functions dynamically, right? So the key is that it shouldn't happen just at startup time, server startup time. It has to happen at, at runtime as well. All right? So if we step back and look at the Bloomberg Spark server now, knowing just this one puzzle piece, we basically have a request handler. It's a listener on a port. We've got a persistent Spark context. And we've got the function transform registry, which contains a critical mass of out-of-the-box functions with their corresponding Spark implementations that are bound with names, and a bunch of user-defined analytic functions that our clients or anyone else cares to contribute into the FTR. All right, let's move on to the second innovation, or the second puzzle piece, if you will, which is the request processor. Right, request processor, they're nothing more than Spark applications that play the role of orchestrators. What a request processor does is it takes a request delegated to it by the request handler based on some routing logic, and the request processor deciphers the request. Once it deciphers the request, it then essentially looks up functions from the FTR and composes these functions. And that's essentially the role of request processor. Very quickly, these request processors come in multiple flavors, right? On the one extreme, there are coarse-grained request processors that have self-contained logic that they don't need to get any other function from the FTR. In essence, they use the Bloomberg Spark server as a hosting environment, but don't leverage any of the publicly available functions. At the middle of the spectrum are request processors that have their own logic or transforms, but they compose those along with the public functions in the FTRs and then affect their analytic, right? But at the right extreme of the spectrum, I envision declarative query-based request processors, right? So think of a request processor that can take a declarative language such as SQL-based queries and assume that this request processor is a cross-compiler that essentially compiles the SQL request into compositions of functions from the FTR, right? That, in essence, is the power of the declarative request processor. And I contend that pretty much all the other flavors of request processors will asymptotically approach the declarative query language. In fact, we are working on something like this internally. All right, so the third and most important innovation is the managed data frame, the notion of a managed data frame. So we saw that the request processor basically translates incoming requests into functional compositions, but it has to apply it onto data frames. Well, the request processor could actually instantiate the data frame or frames that it needs, but we'd be back to square one. Each request processor, in essence, is dealing with redundant code relative to managing the lifecycle of these data frames. Instead, we chose an approach of registering data frames in what is known as a data frame registry. Except data frames are by themselves insufficient for our purposes in here, and let me explain. Well, let's first start out by understanding what a managed data frame is. Right? A managed data frame is basically an abstraction on top of a standard data frame. Right? And basically, it has a name. It encapsulates a standard data frame. But the most important part of it is it contains execution metadata. Right? Now, why do we need this sort of execution metadata? There are several flavors of execution. Let me illustrate a couple, and my colleague will talk about a few others as well. All right, so a managed data frame typically abstracts your standard data frame. So it's not introducing anything. It's not changing the Spark programming model, if you will. So you're still coding to the same Spark APIs. But what is the motivation for creating this abstraction? Well, consider this use case, price analytics, right? So it's commonplace for us to do pricing analytics, find the average price of IBM over the last year, for instance, right? Price analytics typically falls into two buckets. The kind of analytics that requires only 2 years or less of historical data, and then the kind of price analytics that requires perhaps 20, 30 years of historical data, right? And it would be meaningless to penalize the use cases that requires only 2 years worth of historical depth by having the data fetched from a deep store that contains all 30, 40 years worth of data, right? So the way we approach this problem is we have two stores. We have two stores, one that keeps shallow data and one that keeps deep data. But the data frame that abstracts these data are still the same, because the schema is exactly the same. In this simple instance, the schema is just an identifier and the price, right? But what we want to be able to do is we want to be able to capture the metadata that says, if the query is for shallow data, then use this other abstraction, this managed data frame called the shallow managed data frame, right? Shallow price managed data frame. On the other hand, if the averaging is for 10 years or more, then you want to be able to say to the registry, hey, give me the managed data frame, but the predicates that I want you to kind of honor on my behalf is that I need 10 years worth of data. Then a registry, oh yeah, I've got metadata that tells me that I can essentially serve up the deep priced managed data frame as opposed to the shallow one, because you're going to have to need all of 10 or 30 years worth of data. Now keep in mind that these managed data frames can be registered by ingestion pipelines or by other request processors. A request processor could actually represent its results, computational results, as managed data frames and bind them dynamically, allowing for this compositional analytics that's at the base of our requirement, right, in an interactive manner. So what I just gave you was an example of what is known as the data distribution metadata. There's also data derivational metadata, extremely powerful concept. So very often we want to synthesize columns. Adjusted price is a synthetic column that's based off of the base price. And most often this problem is solved through ETL, at ETL time, at ingestion, right? What we want to be able to do is also be able to do this at runtime. There are, in fact, situations where ingest time synthesization of these columns are insufficient, right? So in metadata, you can actually capture through any mathematical expression, valid mathematical expression, what the notion of an adjusted price is. And when this managed data frame is deployed, then the corresponding columns are synthesized. The actual materialization can happen either at registration time or in a lazy manner at query execution time. All right, so to kind of summarize, in essence, you've got the request processor, you've got the function transform registry, and you've got the managed data frame and the registry. Let me hand over to Sudarshan to talk about the flows and also the ingestion manager and to wrap up. Sudarshan.
Thanks, Partha. As we just saw, application developers implement their business logic in request processors, which get deployed and hosted within these Spark server instances. Developers also register data sets at these endpoints, whereupon the framework uses the schema and execution metadata of individual data sets to generate and bootstrap data frames, thus priming the registry. Once the registry has been primed, the Spark Server runtime is now ready to start servicing requests. Within each Spark Server instance is the registry of managed data frames. Within each managed data frame are multiple generations of data frames that are constantly being created and destroyed. The ingestion manager is responsible for creating new data frames and storing them within the corresponding managed data frame in the registry. Each new data frame represents the latest and greatest snapshot of a given data set. In other words, each Bloomberg data set is represented as a managed data frame within Spark. Each managed data frame contains a sequence of data frames, with newer data frames in the sequence representing a more up-to-date snapshot of the data. Request processors request for specific versions of a set of managed data frames, perform transformations on them by invoking a chain of predefined user transforms, and when done, return them back to the registry. When a request comes in, the request handler routes the request to the appropriate request processor based on the endpoints that these request processors are registered at and the path in the request, like is the case with any servlet container. Once a request processor has been invoked, one or more Spark jobs are executed on the cluster, and the results of the computation get serialized and sent back out through the request handler. In the next couple of slides, let's look at some of the support infrastructure that has to be stood up external to Spark required for the functioning of the registry. Bloomberg is standing up an enterprise-wide data pipeline to connect together various data systems. Standardized connectors take updates off the pipe and populate various backing stores, RDBMSs, HBase, Solar, etc. Data in these backing stores, as well as the updates on the pipe, have a well-defined schema and encoding, which is captured in a schema repository. Given a dataset name, our framework uses this schema repository to get the latest version schema of a given dataset. The repository lookup happens whenever an MDF needs to be synthesized, which happens at the startup of the Spark server, but also on demand, as we'll see in a little bit. Schemas are also indexed to allow the registry to look up a managed data frame, not just by name, but by specific data elements contained within it. For example, if an application developer wishes to do some analytics with, say, earnings per share data, he can query the registry for an MDF that contains EPS data, even though he doesn't know which one it is. Data discoverability is a significant issue in any large enterprise, and these are small steps towards addressing that. In addition to the schema, generation of managed data frames also requires execution metadata that Partha briefly alluded to before. Execution metadata also includes dataset source provenance information, such as what HBase cluster is this data stored on, what Kafka topic are updates being published to, and so on. Execution metadata also includes various knobs that dataset owners can tune to control the performance characteristics of their data frames. For example, what is the frequency of data refresh from backing store into Spark for a given dataset? What is the persistence level of the data frames that are created, and so on. In addition to generating managed data frames based on schema and execution metadata, our framework also allows for already constructed data frames to be registered. More often than not, data frames sourced from a backing store have to be transformed by domain-specific business logic before they can become usable in queries. We allow for the deployment of custom business logic within the Spark server runtimes to generate and register data frames resulting from such computations. For example, consider a request processor that needs to do some data modeling that might choose to save a data frame representing model coefficients inside the registry. A peer request processor might retrieve this same data frame to do model QC and validation. Such state sharing allows for collaborative analytics across application workflows, especially true in Jupyter Notebook-like environments. An important capability of the framework is the ability to create managed data frames on demand. Typically, each Spark server instance has data pertaining to a specific data domain registered and materialized within it. So for example, you have the equity Spark server instance with equity content materialized within it, the fixed income Spark server instance with fixed income content materialized within it. But now consider a cross-domain query that might require some equity content and some fixed income content. Such a query could be routed to either Spark server instance. The instance will query the registry and discover that it has only one of the two data frames required to service the query. At runtime, it queries the schema repository and the execution meta store to construct the other data frame on the fly. The data frame that was constructed on the fly could be discarded once the query has been answered. Pre-canned analytics can be easily addressed by taking stock of all the data sets that are queried together and materializing them at the same Spark server endpoint. But such an ability to create managed data frames not already registered at a given Spark server instance is required to support true ad hoc cross-domain analytics. There is a significant long tail to how Bloomberg clients access our data. So typically, only a small fraction of data is used in majority of the analytics, majority of the queries. Hence, not all data records are equal. The low latency nature of a Spark analytics means that we can often not afford the cost of data retrieval from an external backing store. Hence, high-value content is kept deserialized within Spark. Our framework allows dataset owners to specify arbitrary filters at the time of dataset registration. These filters are applied to figure out what records have to be extracted from the backing store and kept within Spark. These filters are also applied to figure out what updates from the pipe have to be absorbed into Spark and what can be dropped on the floor. For example, data pertaining to companies that are members of the most popular equity indices, Dow 30, Russell 2000, S&P 500, can be kept subsetted within Spark. For everything else, we would go to the backing store for data. When a request comes in, the request processor tells the registry what data frames it needs, but also provides the filter predicates, if any. The framework applies these predicates to query the subsetted data frame. It queries the backing store with a complement of the predicate and returns a data frame that represents the union of the two. The request processor is only aware that it was given a data frame with just the records it cares about, but not how that came to be. To illustrate this with an example, let's say for a given data set, the subset criteria is that the company should be a member of the S&P 500. If you got in an aggregation request for 501 companies that represent S&P 500 plus 1, the framework applying predicate logic knows that it needs to retrieve data from the backing store for just a single company, and conceptually rewrites the filter and pushes it down as an efficient point lookup in the backing store. Subsetting provides dataset owners trade-offs in adjusting performance and cost. They can achieve higher performance by having more data cached within the executed JVMs, but would have to pay up more for resource utilization. Subsetting today is static and is defined at the time of dataset registration. In the future, we might employ LRU cache-like mechanisms wherein data starts in the backing store, migrates into Spark upon demand, and moves back out when not used. Subsetting represents one of those capabilities that makes sense to incorporate into core Spark, wherein a data frame abstracts out multiple storage tiers for a given data set, and the Spark optimizer, through pluggable optimization rules, can retrieve data from any of those backing stores based on their capabilities and the query requirements. Next, let's look at some of the techniques we use to keep managed data frames continuously updated. The first technique is periodic refresh, wherein a given data set has a backing store, but no real-time stream of updates. Based on the refresh interval specified at the time of dataset registration, we query the backing store, applying these subset predicates to create new data frames within Spark. These data frames are created at the persistence level as specified by the dataset owner. So he can say, this is high-value content, use 2x memory replication. This is low-value content, keep it deserialized on disk. It's important that analytics be low latency in terms of queries, but also in terms of data updates. As I mentioned before, Bloomberg is standing up an enterprise-wide data pipeline where a number of the core financial data sets are being published to. This pipeline is backed by Kafka, and each data set is published onto a different Kafka topic, which results in a D stream within Spark. So there are as many D streams as there are data sets registered at a given Spark server endpoint. For a given data set, we do an initial data pull from the backing store and then start consuming updates from the stream. As we consume updates from the stream, we merge the updates into the base state that we have subsetted within Spark. We iterate over the RDDs produced in the result D stream, convert these to data frames, and store them within the corresponding managed data frame in the registry to be handed out to queries that come in. I'd like to point out that in terms of intent, this is very similar to structured streaming that's being introduced in Spark 2.0. The implementation is different, but this is streaming not for the sake of producing an output stream, but this is streaming for the sake of updating some state that we want to serve interactive queries off of. Partha talked about user transforms, how user transforms could be registered at a given Spark server endpoint and be referenced in analytics. It's important to note that these user transforms are not usable just in query time analytics, but are equally applicable for ingest time analytics as well. By ingestion here, we are referring to ingestion into Spark itself. For example, Data sets that live in separate hedge-based tables might need to be denormalized and surfaced as a single data frame within Spark. This joined denormalization can be implemented within a user transform that is applied to the base data frames during each data refresh cycle. The results of the user transforms then get cached within the corresponding MDF in the registry. Similarly, we've seen that data representation has a significant effect on Spark query performance and query latency. We've been using user transforms to great effect to prototype and benchmark different data representation changes quickly, rather than having to change the data representation all the way in the backing store. We've noticed that this has a dramatic effect in shortening the development lifecycle of a request processor. The ingestion manager is constantly creating data frames and storing them within the managed data frame. Each new data frame represents the latest snapshot of the data, as we discussed, and fully subsumes the prior data frame. Hence, older data frames can be unpersisted once a new version of it exists. However, it is possible that a request processor is still operating on an older data frame, and unpersisting it might lead to non-deterministic performance degradation, as some of the lost partitions of the older data frame have to be reconstructed by walking back the lineage. We solve for this by having managed data frames keep track of which data frame versions are being used and who are they being used by. The older data frame is unpersisted only once its reference count is 0 and a newer version of it exists. Often, client applications make multiple requests into a given Spark server instance. These independent requests represent separate analytics over the same base data sets, with the results of the analytics blended on the client side. Given that data is constantly changing underneath the managed data frame, if these requests came in slightly staggered, it's possible that they might see different versions of the underlying data. Since it's important that independent requests be allowed to operate on the same data snapshot, managed data frames associate data frames with the time epoch of when they were created. The registry allows for a reference time to be passed in, whereupon a data frame with time epoch equal to or less than the reference time is retrieved and returned back to the request processor. Thus, a common reference time in requests allows for the same data snapshot to be used, despite data constantly changing under the hood. Bloomberg is looking to use Spark in a low-latency interactive context, wherein Bloomberg clients directly interface with Spark-based analytic engines that respond in hundreds of milliseconds. At the same time, these Spark server applications consume multiple incoming streams of data, minimizing the interaction effects between query and ingest while balancing the twin goals of low-latency data updates as well as low-latency queries is a challenge. The challenges around performance consistency, the challenges around availability. Bloomberg is looking to make contributions to core Spark in some of these areas, especially high availability. Our very first public contribution is Spark 15.352, which is to add topology awareness to RDD block replication. These challenges notwithstanding, we believe we have a framework in place that allows Bloomberg application developers to craft Spark applications with an eye towards composability and time to market in the enterprise. At the same time, Spark augmented with such a managed data frame registry allows for data to be pulled together from disparate data silos and is a powerful enabler for cross-domain analytics. It's still early days for Spark deployments at Bloomberg. We look forward to hearing your feedback and inputs on these architectural recommendations. Thank you.